In enterprise IT, hardware follows a strict biological clock. Within 3 to 4 years, a server is ripped out and written down to zero. The speed of artificial intelligence development makes the cycle seem even faster. When models like GPT-4 or Claude Opus launch, they demand massive increases in computational power. The math implies that last year's hardware cannot keep up with this year's models. Yet, if you look inside the world's largest data centers today, the previous generation of silicon is not being thrown away. It is actively processing queries at the absolute cutting edge of the AI frontier. Older architectures, specifically NVIDIA's Ampere and Hopper chips, are being repurposed. Their economic utility is shifting based on how they're physically deployed in the rack. A structural change in how engineers physically process AI queries allows legacy hardware to remain relevant for years, significantly extending its useful life before the silicon eventually degrades. To see why, look at the scale of capital expenditure in hyperscaler data centers. Hundreds of billions of dollars are locked into existing physical fleets. For training a brand new frontier model from scratch, this older hardware is too slow. But for inference, the act of running a trained model to generate an answer, this installed base holds massive hitting value. Inference consists of two distinct physical actions, stitched together in real time. Treating those two actions as one unified workload is the error driving the incorrect appreciation models currently affecting private credit markets. Accessing the latent financial value in this hardware requires splitting the inference workload into two distinct physical bottlenecks. Semiconductor architecture is governed by three nodes: compute, memory capacity, and memory bandwidth. The laws of physics dictate that you cannot maximize all three at once. If you optimize a chip for massive compute, you are physically forced to make trade-offs in either capacity or bandwidth. Over the last decade, legacy GPUs were designed to handle a wide variety of tasks. To do that, their architecture favored large memory capacity over ultra-fast, specialized input and output speeds. Today, a wave of new AI hardware startups is attempting to challenge NVIDIA by making entirely different trade-offs on this triangle. These specialized chips fail as general-purpose GPUs, but if they are tasked with handling only one specific half of the inference equation, they become incredibly dominant. Processing a prompt involves two distinct physical stages: prefill and decode. You can think of these two stages like operating an 18th century naval cannon. This visualization represents the prefill phase, which acts like loading the cannon. The model is taking in massive amounts of prompt context, maintaining its own state, and mathematically understanding the input. This means the prefill phase is strictly capacity-bound. The hardware needs a large physical space to hold all that context at once. Decode is firing the cannon. This is the process of generating the new response tokens sequentially, pushing them out one by one. Decode relies entirely on memory bandwidth and I/O speed. It is not constrained by capacity, but by how fast the hardware can eject the generated tokens. It is strictly bandwidth-bound. By decoupling these two phases, a process called hardware disaggregation, engineers can assign specific hardware profiles to each distinct bottleneck. When you physically deploy a disaggregated architecture in a modern data center, the hardware looks very different from a standard server rack. On one side, you have specialized decode hardware, like the wafer-scale chip designed by Cerebras. These systems are built around maximizing memory bandwidth and I/O. Because they don't have to dedicate physical space to memory capacity, these specialized chips process the decode phase exponentially faster than any traditional GPU. On the other side of the rack, you have the legacy hardware. NVIDIA Grace Hopper and Ampere boards provide the massive memory capacity required to anchor the prefill phase. The data flow is sequential. The older NVIDIA GPU digests the initial prompt and holds the context state, then passes that state over to the specialized chip to generate the output. Because the older GPU is exclusively tasked with prefill, its lack of cutting-edge token generation speed becomes irrelevant to the system's overall performance. This physics problem directly dictates hardware economics, particularly for the private credit markets that finance the recent AI build-out. This depreciation curve shows the baseline assumption of the private credit market. Billions of dollars in loans were underwritten on the expectation that legacy GPUs drop to zero residual value within 3 to 4 years. Hardware disaggregation completely rewrites that financial math. assigning legacy GPUs exclusively to prefill tasks, extending their useful life significantly beyond the typical 3-year write-down, potentially lasting as long as the silicon remains physically viable. Extending the useful life of an asset mathematically lowers its cost of capital. This shift can bring GPU financing rates down from the high 7s into the 5 or 6% range. Disaggregation offers a hedge against massive write-downs by extracting years of additional utility from the existing installed base. Future data centers are scaling through highly optimized hybrid architectures that integrate varied hardware profiles. Accurately projecting the economics of AI infrastructure requires understanding the underlying physics of these compute bottlenecks. Existing compute fleets now serve as the foundational, value-generating layer for the next decade of AI inference.